But seriously, we are going to build some crystals. So, since our building blocks are pretty round, we are going to build different crystals. Let's start with the simple examples. I just take 4 balls. I ask you to be my assistant today. Okay, now I can do different models, right? The first model I can do is just a primitive cubic cell. First cell we are constructing is the primitive cubic cell. Primitive cubic cell. Now I'm going to measure our primitive cubic cell. You see that the distance between the middle of the ball to the middle of the ball is the same size like the distance of the diameter of the ball, which is around 7 centimeters. I just make sure it's 7 centimeters. Well, this one is showing 6. Let me do it exactly. Any chalk from one place to the other place. No, it's 7. Okay. 7 centimeter is the diameter of the ball. Okay, so now our primitive cubic cell that looks like that and has the balls in the corners has this distance of 7 centimeter, right? Because that's the distance between the center of the ball and the center of the ball. Okay, the total volume of this thing is then 7 centimeters times 7 centimeters times 7 centimeters, right? Okay, now what is the total volume inside this cell, occupied by the balls? Well, you see that you have 1/8, another 1/8, another 1/8. So totally you have 8 times 1/8 times the volume of the ball, which is equal to 4/3 pi r square cube, right? This is the volume of the sphere. How much it is? We know that r is 1/2 of this. So r is equal 7/2. I plug it inside and I find that this is equal to 4 times pi divided by 3 times 8 times 7 times 7 times 7, right? So now we have to find what is this. How much is this? Somebody can calculate? $3.1, around 12.4, 0. Okay, so we see that field space is 52.3% in this crystal, and the empty space is 47.7%. Good. Now we are going to the next one. This was the cubic primitive. Now we are going to the cubic body-centered. What was for the body-centered? C? I. Cubic I. So again, we have on the corners 1 atoms and 1 in the middle. Good, let's build this model. That will be more difficult now, because we have to keep all the, okay, we start with the 4, right? Okay, we'll collect them later. Now I put 1 here inside. You need more hands. And now we put another 4, but they must touch each other. So maybe try to, yeah, and we put another 1, this 1, this 1, this 1, and this 1. Okay, now we have to play. I know 2 hands are not very enough for this, but this distance, and this distance must be the same. Let me check. Now it is 8.5 centimeter. Well, kind of good. Yes, nice model of the. Okay, so we had now this 8.5 centimeter. So we found that for this one is this. Now we are going to calculate similar story for this crystal, and we know that the diameter is 8.5 centimeter, and we know that the volume occupied by balls is again 8 times 1/8 plus 1 times the 4/3 pi r cube, which is equal to 2 times 4 times pi over 3 times 8 times 7 cube centimeters. Okay. So now, what I'm asking to calculate is calculate the volume of this one. So the V is equal d to the power 3, which is, somebody's calculator, this one to the power 3. 13. Okay, now I understand. Thank you. Good. And this one? Three, 5, 9. Cubic centimeters, cubic centimeters. Now, can you divide these two numbers? %. Empty space is only 41.5. Okay, so comparing these two results, this one has a lot of empty space. This one has much less empty space. So there is a question, which structure has the smallest number of empty space? And turns out that the structure with the smallest amount of empty space is the is the cubic F structure, and we are going to show it. So first, how it looks like, you should remember. It again has the atoms in the corners, and except of that, it has also the atoms in the middle of every wall. One more here and one there. Terrible. Now we are going to build this. So maybe we need one more assistant, I don't know. We'll see. Okay, so first, okay, just let them go. We'll correct them later. So we start with the first layer. In the, is correct? Yes, this is correct. Okay, now the next part, we are going to put one of them here. You are controlling that these balls that he's putting are not going away. So put one hand here, one hand here. 1, 2, 3. What I should measure here? Doesn't look good. I mean, this layer looks good, this layer looks good, but the last fourth one is one more in the middle. You're right. Yes. Looks good? Yeah, not bad. So now, which distance I should measure? Let's measure this. It is 10? Yeah, it looks like 10 centimeters. So what I have here is diameter is 10 centimeters. And now the number of the taken by the balls is 8 times 1/8 plus 6 times 1/2 times 4/3 pi r3. This one gives me 4, so the total volume is 4 times pi over 3, 8 times 7 cube, which is you should make a camera and a photo of your model. Becoming stable. 718. Correct? Good. Now this one at least is easy. So the other volume is 1000. So I have the field space is 71.8% and empty space is 28.2%. Thank you very much. 2 assistants, I still need you. Okay, thank you. Now, we have to prove this is the highest possible field space. That will be a bit difficult, and for proving this, we are going to build a bit larger model. First, before I start here, I will be working on the blackboard. One of the way of putting the next layer, okay, I don't have to convince anybody that this is probably the best packing in one dimension. The balls are close as possible. Now we are working on the other dimension. So one of the way of putting the ball is here. But everybody sees when I put it here, it goes down. So this is the best for 2 dimensions. Okay? So you see that if I put the next layer, I'm getting something like hexagon here. Okay? 1, 2, 3, 4, 5, 6 with 1 in the middle. Okay. So now I'm going to put this hexagon structure on the table. Nice, nice. put this here. Yeah, looks good. Maybe try it even larger, because it's pretty stable. You don't have to really keep just pushed together. Okay, maybe two more and we are done with the first layer. Okay, this is definitely the closest packing in 2 dimensions. Now we are working on the 3rd dimension, going up. But somebody tells me it's boring, there is nothing to do there, because of course, obviously I can put the ball here, or between them. Closest, this is the best, right? Lowest energy. So I'm just putting many of them again, making the 2nd layer. And somebody who sees it may say, that's the end. The next one will be again the same, and the next one will be again the same. This is the closest packing, right? But the point is that it's not true. Because if you look from the above here, down, and I want each of you to come here and see, you can see the ball there, or you can see empty space there. Just go one by one and see that there is a difference between the holes that we have. Some of them have the ball under, but some of them they don't have the ball under. You see? Here you can see the ball, but here there is nothing. There is empty space. My point is that the next layer can be put above the ball that is down, or it can be put above the space. And both of these structures have different symmetry. They have different Bravais type, turns out. And we are going to find what they are. Both of them are called the close packing structures. Close packing means that the balls are as much closed packed as possible. But now, depending on where I put the next one, we can have either hexagonal closed packing or cubic closed packing. The hexagonal closed packing structure is usually written as HCP for the first letter, HCP. Cubic one is usually written as CCP. So there are two possible closed packing structures. Well, when somebody would say two possible, somebody else probably say maybe more than two. You can put the 4th layer again in different possibilities, and the 5th one again in different possibilities. To be honest, I don't know. I never analyzed these possibilities. Usually people say only these two are possible. Maybe true. Okay. Now, we have to draw the Bravais type for all of these types. And we start with hexagonal one because it's easier. So I destroy a bit our structure because we don't need so many now. Okay. So we are going to do once again the one layer, but in much smaller scale. So we said this one is always the same. We also said that the next layer is always the same. So as so far this part is always the same. Now the difference comes, okay, this one is of course always the same, the middle one. But the difference comes where I put the next 6. And the next 6, maybe I just do with 3 first. The next 3 can come here, or they can come like that. I'm lost. Like that, or like that. By 30 degrees difference. Entering this hole or entering this hole. Yes. Let's say that they are exactly above these bolts, exactly above this. 1, 2, 3, 4, 5, 6. Looking from your perspective, that will look like that. 1, 2, 3. It's a difficult job. Oh. Okay, I try to write down on the blackboard what I'm getting. So I see that in this this is the first layer. Now I'm putting the second layer, and we already said the second layer comes here, here, and here. So this is the second layer. Now I'm putting the third layer. And in the hexagonal packing, the third layers come exactly the same positions. Like this one. This is a view from the top. Now instead of drawing the view from the top, I'm trying to take only this part. Of course, in the orange one has one more to here, and these connections. So now I'm taking this part, and this part looks like that. 1, 2, 3, 4. Now this one should be orange because these are 2. Now and I'm getting this structure. Now the angle here is 60 degrees, and this is clear from this one, right? And the angle here is 120 degrees because it's this one. Now the angle here is 90 degrees, and I think it's obvious for everybody, and also the angle there is 90 degrees. Now this one and this one has the same length because there's triangle with the equilateral triangle. So this one and this one must have the same length. This and this is the same length. But this one is different. Everybody can see this. See. This is perfectly the hexagonal structure that we draw in the last class. Good. Now I do the different story. Instead of putting this ball in the place where the ball was in the previous layer, I'm putting it in the place where there was empty space in the next one. So maybe it's not true that this one must be in the middle. Yeah, probably no. Yeah, that would be difficult to build. So we just skip this part of building. I just have to draw it. In the other model, I'm starting with 6 again. 1, 2, 3, 4, 5, 6, 7. Then I'm building the yellow one, the next one. That will be here. Now I need the third layer. And the third layer here was orange. So let's keep the orange. Now, the next atom, I cannot put it here because it would be hexagonal. I have to put it in the place where there was nothing, so here. Another place like that is here. Another place like that is here. And now I'm building the next layer, the fourth one, which would be blue. And that would overlap with this one. I got something terrible. You cannot see probably anything. So now I'm going to take the red chalk. And I'm going to show you that this one is cubic, which may be a bit difficult, but try to look. The first ball is connected to the second layer like that. Good. Now, this second layer is connected to the third layer. Like this, and this is connected to the first layer like this. Everybody can see the cube? Or not really? Who can see the cube? 1, 2, 3, 4. Good. We are going to build the cube then. The first layer is 6. I'm interested in this corner. When I have a cube, this one is going to belong to the first layer. This one, and this one is going to belong to the second layer. This one, and this one will belong in the third layer, and this one will be in the fourth layer. So this is number 1. Now I'm putting 3 number 2s. Okay? You have the lower one going to this 3. Now I'm putting 3 number 3. And now I'm putting number 4. Doesn't look very convincing, huh? I know. Maybe the reason for this is that this must have some spaces here. And then these balls come closer down there. Yes, probably that's the answer for this question. Which would be only 3 of them, right? Still difficult to control. Or very difficult to control. Yeah, we give up. But, okay, so, yes. So now this one is in the first layer. Is at the bottom, in the middle, down there. 2, I have the yellow color, is in the second layer. 3 is in the third layer, and 4, which is blue, is in the fourth layer. Good. But this is a primitive cell, right? But we are not going to have a primitive cell here. We are going to have another cell. That's why we couldn't build it here. Yes. Maybe it's even more complicated. I'm sorry. Even more complicated. Start once again. 1, 2, 3, 4. So this is in the first layer. Now I'm forgetting that this cubic is not just primitive cubic, it's the face center cubic. So another one, the closest, must be in the middle of every wall. 1, 2, 3. Difficult to see, but I mean that this is in the middle of this wall. It should be here. I'm not good at drawing. When you take the first 6 and put the next 3, you put the 6 again on the top, but the next 3 on this 6 would be rotated like that. And then this is the lowest one is this. Then the next 3 are these 3. The next 6 would belong to these corners and middle of them. I guess everybody has to do it on. It's very difficult to build. But anyway, that would be the face-centered cubic cell. I'm afraid I cannot show it today. I try to think how to show it next time. Maybe I can do it. Anyway, we found this percentage. We found it by measuring. Okay? Now I show you how to find this without any measuring, just by simple calculations that it must go that way. Let's take primitive cubic cell. It's not a very good one. Once again, 1, 2, 3, 4. 1, 2, 4. 1, 2, 3, 4. Good. Now it's a bit better. Now I know that this atom is here. This atom is here. This atom is there, and so on and so on. So if I draw just this wall, we see that we have the atoms like that. So now I can see that the size of the box is just this line is d cube. The size of the atoms is just 8 times 1/8 times 4/3 pi r3. But I see that r of my ball is nothing else than 1/2 of d cube. So now the filling is nothing else than V atoms divided by the V box. Okay? I can calculate this one a bit. This one gives me 1. And this one gives me 4 pi over 24 d third. So V atoms is 4 pi over 24 d cube divided by d cube, which is 4 pi over 24. And we calculated this one already, and it was around 51.2%, right? $52.4, right? No? Yeah. Okay. It's a bit more difficult to do the same calculation for the other cell. For example, when we take the cubic body-centered cell, we have one atom in the middle, and we have the atoms in the corners. But when you have the atoms in the corners, of course, we just always assume that they go as far as possible. Now, if they would go up to here, in the middle, if these two would meet, there would be not enough space for this middle atom. So it turns out that they cannot really meet. It means that if you make this line from this corner to the opposite corner here, this is the line with the largest packing. It means this atom would go to the half of this line, maybe here and here, and this atom would go up to half of this line. Right, so I'm starting again. Volume of atoms is again 8 times 1/8 plus 1 in the middle multiplied by 4 pi over 24. Yes, but now I'm going not to use d anymore. It's just 3 pi times r to the power 3. Which is equal to 8 pi over 3 r to the power 3. where r is the radius of the atom, r. Now I see the next thing. I see that the distance from this point to this point is equal 4r. And this distance from this point to this point is nothing else than d square plus d square plus d square, where this is d. Is it difficult or not? Yeah, you understand why this is that, or somebody wants me to explain? If somebody wants to explain, ask now. Everybody understands? Oh. So this is equal to cubic root of d. So I'm finding from this that d is equal to 4 over square root of 3r. So now I can calculate the v box being equal to 4 over r to the third. And I'm finding filling in this case. Filling would be equal what? This divided by this. This one can be a bit simplified, I guess. 4 times 4 times 4, 8, 32. 16 times 4, no, 64 divided by 3 square roots of 3 r to the third. When I divide these two things, I'm finding 8 pi over 3 divided by 64, 3, 3, which is 3 is, this one goes to 8, there is 8 here, and upper part is square root 3 times pi. Somebody can calculate this? 0.68. Once again? 0.68. Which is 68%. Correct? And supposedly this should be identical to this. No, not to this. It's deleted, but it's not. We got 58% in the other one calculation from the measurements. I had problems with the volume of one of the crystals. We calculated something and it was not exactly the same what we measured. So after I came back to my office, I did once again the experiment with the tennis balls. You remember probably, we had the crystal when the atoms were in the corners. And except of that, there was one extra atom in the middle of the cell. Well, and we measured the volume and we did the calculation. We found 58%. 58% is full. But then we measured. Then we did the theoretical calculation and we found it 68. Why such a big difference? After coming back to my office, I just started from the simplest. I just measured the diameter of the tennis ball once again. And turned out that 6.5 centimeters, not 7. Well, after plugging this one in the equation, I found 68.2%. So this was just simple experimental error in measuring the diameter of the ball. I think we measured it to be 7 centimeters in the classroom. Or maybe 6, I don't remember. Maybe 6. Yeah. So we got the wrong 58%. Okay. So I'm glad that this one is solved. Turns out that for all the other crystals it didn't matter because we made the size of the unit cell dependent on the size of the ball, and the size is cancelled. So that was the only case where the size didn't cancel and we got the experimental error propagated to the occupants of the cell.